All right, today in class we started looking at oxidation numbers. We started looking at ions more closely. So here are some notes really quickly. If you were not here today, these may help a little bit more. The very first thing that we did is we didn't necessarily take these notes, but we went over these concepts. So here's some things just to kind of get you started. So the first thing is looking at what is an ion. And if you remember, and you can pause this video at any time if you need to get the definitions down, but remember, an ion forms when atoms become charged because they have gained or lost an electron. And that is super important, that it's an electron, not a neutron or a proton, because if you lose a neutron, it becomes an isotope, not an ion. If you lose a proton or gain a proton, it becomes a whole new element. So we are just talking about ions and electrons, so those two words should always kind of go together. So a positive ion, which we've talked about in class before, and again, pause this if you need to get the definitions, but a positive ion forms when electrons are actually lost. So you're giving away, remember, electrons have a negative charge. So if I'm giving away an electron, I'm going to become overall positive. So for example, if I have 6 protons and 6 electrons, protons are positive, electrons are negative. So that's really going to give me, if I add those together, that's going to give me 0. But if I am giving away one of these electrons, I would still have my 6 protons, because remember, I would be changing the atom if I didn't, changing the element itself. If I gave one away, I may only have 5 electrons. Okay, so if I added the positive 6 and the negative 5 together, I'm going to end up with a +1 charge. So that's how I get to be a positive ion, because if I'm losing or giving away electrons, so same thing, 6 protons is the same element. This time if I give away 2 electrons, I'm going to have a +2 charge. So that's the basic concept of what happens here. So negative ions are the opposite. If I gain an electron, so if I take that same example and we look here, if I have 6 protons and 6 electrons, that's going to zero out. But if I gain an electron, 6 protons, and now I have 7 electrons, that's a +6 plus a -7, I'm going to end up with a -1 charge. Okay, so they become negative ions. So the same thing there. If I add another one, +6 plus 2 negatives, or plus 8 electrons, then I would actually end up with a -2 charge. Okay, so that's how you form negative ions. Then we talked about also in class what the oxidation number is, and an oxidation number is going to actually tell you how many electrons an element will gain or lose when they're bonding. And we're going to put these on the periodic table of elements. So I listed them, so you can pause that and get that if you need to. I actually listed them here, that you can pause and write down if you want to. But we are going to put those on the periodic table here in just a second. And then the types of ions, this is kind of important. If you have a non-metal, those are always going to make negative ions because they're going to gain electrons. Metals are always going to make positive ions because they're going to lose electrons. So let's get out our periodic table and look at our oxidation numbers. So what we did in class today is that we added these yellow numbers on top of our valence electrons. We've already put these valence electrons on here before, so you should have it where family 1 has 1 valence electron, family 2 has 2 valence electrons. Your transition metals, the valence electrons vary, and so on and so forth. 3, 4, 5, 6, 7, and 8 valence electrons. So what we did today is we came back and we put in oxidation number. So your oxidation number will tell you if this family is going to give away or take electrons, or gain, right? So they're going to lose or they're going to gain electrons. It's going to tell you how many. So first of all, we have to think about what you call the octet rule. Remember that all families are looking to have 8 valence electrons to be stable. So when we look at family 1, let's talk about family 1 really quickly here. Family 1 is here. Family 1 has 1 valence electron, okay? So they have 1 electron, and they need 7 more, right? So they need to be at 8. So this is what they need, and this is what they have here. So always think about tug of war. If I'm looking at 1 person on this side of the rope and 7 people on this side of the rope, it's going to be a whole lot easier to pull that 1 electron over to that group, those forces that are pulling. So in this case, because we're family 1, it's going to be really, really easy for them to lose that electron to another atom or another element. So they are going to have the 1+ charge because they're giving away. So again, lithium has 3 electrons, so it's going to give 1 away, and it's going to become an overall positive 1 charge. So if I think about the lithium atom, lithium has 3 electrons. It has 3 protons, right? If I add that together, that's 0. But when it bonds, because it needs 8 to be total, it has 1 valence electron. Remember, lithium, the first shell will hold 2. The second shell will hold 8, but lithium only has 1 out there. So this one's just sitting there, so it needs to go away one way or the other. Either he needs to fill up with 7 more to be 8, or he can give this away and go down to just 1 energy level. So what it wants to do is just give that one away. And so when it gives it away, we've changed this to having 2 electrons, 3 protons, which is going to give me a positive 1 charge. So that's kind of the way that works. So everybody in family 1 acts the same way. They all have 1 valence electron.
I need you to release the tennis team at this time. Release the tennis team at this time. Thank you.
Family number 2 is going to fit that same pattern. So family number 2 has 2 valence electrons. Again, it's a whole lot easier for them just to give those 2 away than it is to get 6 from somewhere else, because they have 2 and they need 6 more to be stable, because remember the magic number today is 8. So they have 2 and they need 6. They got to figure out how they're going to do that. So they have 2, and if they just give them away, they become a +2 charge overall. Now, our transition metals here in the center, because their valence electrons vary, their oxidation numbers will also vary and change. And then up here, family 13 has 3 valence electrons. Again, they would need 5 more, so it's a lot easier for them just to give those 3 away, so they'd have a 3+ charge, and they would end up with 8 there. Okay, if I look at family 14, they have 4. They're going to have a 4+ charge. They're kind of in the middle there, and then it changes turns. So this one has 5 valence electrons. They're going to take on 3. So when they take on 3, they're gaining 3 negative charges, so that would give them 8. They have 5. They're going to grab 3 from somewhere else, and that's going to give them a -3. 16 has 6 valence electrons. They just need 2 more, so they're going to gather them from somebody else. So they'll have a -2. 17 has 7. Do you need to pass? Okay. 17 has 7 electrons and a -1 charge, because basically they just need 1 more to be stable, so they're going to get 1 from somewhere else, so they're going to come up with a -1 charge. And then your noble gases over here, they have 8 electrons in the outer shell. Remember, 8's our magic number. It has 8. It's not going to give any away. It's not going to take any from anybody, because it is stable. So they are not going to make ions, okay? So there is 0. So what we did in class is I gave the students today this sheet, and we went over, you can get one of these from the orange crate if you need to. If you've lost yours, I'll zoom in a little bit there. When I look here, we went over all of this, which is basically what we just went over on the periodic table. It gives you a rundown on the oxidation numbers. They're going to vary right here in the transition metals. Oxidation number tells you how many electrons an element will gain or lose. Okay. We drew attention to this word inert. We read right here about the family 18, how it does not bond, doesn't make ions, because they're stable. Inert means they're stable, not reactive. Okay, we talked about that. We also pointed this out. So if you notice on the trend on the periodic table, these metals that are all over here are positive. Okay, so metals are always going to form positive ions right here. It's important because they're going to lose electrons. And then on the other side, this side of the periodic table, they're going to have negative ions because they gain electrons. They're pulling them to them. All right, then we talked here. So we went over that, and then we talked here about the sign, the notation that we have. Chemical symbol, okay? We talked about the difference in writing it like this and writing it like this. This is showing you nitrogen bonding with something else, which really doesn't exist. Anytime you see a capital letter, it means that there's a new element. So we don't write sodium like that because that's not right. That's nitrogen bonding to something, okay, which again doesn't exist. We have to write it with a capital and a lowercase because Na is for sodium, N is for nitrogen. So cobalt and carbon monoxide are one thing. Carbon and oxygen can bond together and make carbon monoxide. If I put a carbon, it's not really carbon, but if I write it as CO, this is uppercase and lower. This is the element symbol for cobalt, which is totally different than the compound carbon monoxide. So we have to be careful there. We also talked about the oxidation number is always written like an exponent, and the number of atoms is always written as the subscript. Okay, so the subscript is down here. Then we talked about, or it shows you here, how you write them and why it is what it is. So magnesium is in family 2. If we look at our periodic table, magnesium is here in family 2, and it tells us it has a +2 charge. Okay? So right here, when we write that, magnesium has a +2 charge like an exponent, and the reason it is because it lost 2 electrons. Oxygen is in family 16. So family 16 has an oxidation number of -2, so we write it like this, well, as an exponent, and it gained 2 electrons. Over here, the subscript, that's a word, the subscript is talking about this number that's at the bottom. So you notice there has to be a difference in your oxidation number at the top, written like an exponent, and the subscript, because it tells you the number of atoms at the bottom. So our subscript, O2, tells me that there's 2 oxygen atoms bonded together. So oxygen atoms bonded together may look like an oxygen atom here bonded to another oxygen atom here. Okay? Now, right here, it looks like H2O, which is our compound for water. It's our compound, our formula for water. So H2 means that there's 2 hydrogens bonded to O. And if it doesn't have anything there, you have to assume it's a 1. So I have 2 hydrogen atoms bonded to 1 oxygen atom, which means I have 3 total atoms in that compound. So H2O may look something like this. I have a hydrogen atom bonded to an oxygen. Sorry, redo. I have an oxygen atom bonded to 2 hydrogen atoms, or 2 hydrogen atoms bonded to an oxygen. That's the way that would look. 2 hydrogens, 1 oxygen. Okay? But I notice that I have 3 atoms, and these things right here, sometimes they'll be touching, but those are showing that they're bonded together. SO4 is a sulfate, which means I have 1 sulfur atom, even though it doesn't have a 1 sulfur, 4 oxygens. Okay? And those bond together to make a sulfate. Okay? Then Lewis dot structure we went over, which we've been over this before. The dots represent the valence electrons. Okay? So neon has 8, so there's no openings. There's only kind of 8 spaces to go around, and it will not react with other elements. Oxygen has 6, so there's 2 openings. So it means it's looking for 2 more to be full. So it's looking for something with 2 electrons to give away, or it's looking for an atom with 1 that can give it to it twice. So like H2O, hydrogen has a 1 electron to give away, so it's going to give, it's going to bond twice. So a hydrogen atom here, and it can also take on another one. So that's why we have water like that. All right, magnesium is showing you just right here how you can write the Lewis dot structure, Lewis dot diagram. Electrons can move around for bonding, so you can put one dot on the top and one dot on the bottom. That's right. This is also correct. One on the top, one on the left. And it doesn't really matter about that. And then over here, the X can be used to keep track of the electrons from other atoms. So you'll notice that chlorine has 7 and lithium has 1. So lithium is actually giving that electron away to chlorine, so it's noted with an X. So that X came from, it is an electron as well, but it came from lithium, okay? Then we went over this in class today, and here's the answers. I would like for you, if you've been out, because we went over this today, to do this side right here, and then you can come back and check, and you can pause it. So I'll pause it on, this is the first section on definitions, so those are the answers, so pause that and be sure you have the correct answers. All right, the next section here is the oxidation numbers. So these are oxidation numbers here, and this is how it's written with an exponent, like as an exponent. The correct ion notation is what that's called. So pause and fill in or check it. If you have questions, come see me. All right, the next section here, how many atoms? So when we look here, this one says how many chlorines do we have? In this case, we have 2 chlorine atoms looking at the subscript. Oxygens are 1. Aluminums in this case are 2 looking at just the subscript. On this side, we're looking at total. So I have 1 magnesium. Remember, it doesn't have anything there, so it's a 1. 1 plus 2 chlorine atoms gives me 3 total atoms in that compound. So pause, check your answers. Over here, this one, what we did is we said how many are they're either lost or gained. So here's your answers here of how they got the oxidation number +4 because it lost 4 electrons, gained 3, so on and so forth. Our Lewis dot diagrams over here. This is just an example. If you have your dots in separate places, as long as you have the total number of dots there, it'll be fine. Your valence electrons. Here's your answers to that little square. And again, your valence electrons are on your periodic table. So don't forget that you have 2 numbers noted. Like family 1 has 1 valence electron. It has a +1 charge. Over here, family 17 has 7 valence electrons. Remember, we put that on when we first went over it, and 1 negative charge. So there's that. 3 different Lewis dot structures for nitrogen. Doesn't matter, it just has to have 5 around it. This section here, this one is not correct because beryllium only has 2 valence electrons. On these, you have to just put your squares where you have an opening. So you would have a total of 8 squares and dots. So there's 6, there's that one. And then on this one here, it shows lithium and oxygen together and how they combine. So this is one way to show it, and you can also see that oxygen has a separate, another little space. So when this combines, you actually have 2 lithium atoms that will bond to fill in those 2 blanks of oxygen, okay? So we're going to go on to this side tomorrow. Block 3, if you're in block 3, we started doing this today. I'll just do a brief explanation. If you're in block 1 and 2, we didn't get this far, so you can stop. Blocks 3. One thing that we talked about is those transition metals, and we went through and did some of these. The transition metals are going to give you a Roman numeral, and that is their oxidation number. Remember, metals are going to always be positive. So they're going to always give away. So they'll always be positive because they are all transition metals. And the Roman numeral will tell you how many. So zinc 2 is a zinc with a 2 positive. Chromium 3 is chromium 3 positive. Titanium IV stands for 4. Remember your Roman numerals. Titanium 4+. Iron 2, Fe2+. So those are telling you how many, and they'll always be positive. Okay? Now, on the back side here, what we did is we talked about sodium, and you've got an ion, and you've got the formula. One of the key things is if it is a positive ion, okay, if it's positive, the answer is always going to be a sodium ion. Okay, it's always going to be the name of the element and the word ion. Okay, there's no fancy names. If it's negative, so anything when you come down here, if it has a negative, it's going to change. The ending's going to change if it's negative. It's going to change from a bromine to a bromide. Okay, so your ending is going to change to IDE every time. So we're going to write that at the top right here, write that rule. So positive ions will be the name, okay, and then ion. That's how we do it. Sodium ion, right? And then if it's a negative ion, we are going to change the ending to IDE. So you just kind of have to get used to that. So chlorine's negative, chlorine's going to become a chloride. Oxygen's negative, so it's going to become an oxide. All right. So that is how you name those. All right. I hope that helps you review, and we'll get to go over those tomorrow.